So to start off with a question, this is actually the question in your book, okay? I'll just try it out, okay? I've tried a lot of time. So what I'm gonna do is actually the first step is to change s is equals to j omega, okay? So what I do is, I switch all the s into j omega, which is what it is over here, right? The next step is to define the corner frequency, okay, using this formula. So how do we do this? If you take a look, this dude over here is tan j omega, okay? So the tan is a coefficient of the omega j, right? So let's say tan is equals to a omega j. So this a, okay, is actually omega c equals to 1 over a. Alright, so the corner frequency is actually 1 over a, which is the coefficient of this. So in this manner, what I can rewrite is that this is the tan, okay, tan 1 plus, okay, I'm just throwing this, and then in this case I want to get a corner frequency, right? So it's 1 over a, right? So it's 1 over 10 multiplied by omega j, okay? So this is actually the corner frequency, alright? So likewise, if I were to do this, okay, I were to continue. Okay, this is now in this case the coefficient is actually 1 over 10, right? So now in this case maybe like b is equals to omega j. So b is 1 over 10. 1 over 10 is actually equals to b. So 1 over b is actually 1 over 1 over 10, which is equals to 10. So the curve frequency of this poles in this case is actually 10, right? So 10 omega j square. Alright, so we have defined the corner frequency. Okay, maybe I should write neatly. Okay, so I've defined, so the omega c1, okay, which is the zeros of the omega c, okay, is 1 over 10. And this is the 1 over omega c2, which is 10. Alright, so in this case, to write things in a neater way, what I'm gonna do is, so I write this in this manner, okay. So this is exactly the same thing. 110 is actually omega c1, right? So I just bring this down. Okay, so what I mean is that if I were to bring this 10 out and then this omega c1 down, I'll have 10 equals to 1 omega c1, right? Ci, right? So in other words, 10 is equals to 1 over omega c1. So 1 over omega c1 is actually this dude over here. But nonetheless, and the values is all the same, okay? If it's 1 over 10, it's 0.1, right? If I put over here, okay, if I put over here, if I put my omega c1, okay, at this bottom over here, I'll have 10, right? So what is this 10? 10 is actually this 10 j omega, alright? So it's just simply how you want to do it, okay? So I just rewrite in terms of this, where you can just straight away rewrite this. When you see this equation, the first thing you do is to rewrite into this form, okay? You rewrite into this form, and then you define your omega c1. Okay, you define omega c1 and your omega c2, or whatever, omega c3, c4, c5, whatever. Okay, so if you don't understand, you can just go back and then you just reloop. Okay, then I already clear off the j's, so in order for things to be neater, alright. And then next is that I want to plot the different gains in the gain, okay, the k, the gain of the poles, the gain of the zeros, and the gain of the integrator. So what I do is, gain of k is equals to 10, okay, as you know this is the 10. Okay, if I were to just bring this dude down over here, it would be a lot like clearer. So k equals to 10, 20 log 10, you can just use the formula, you get 20 dB. So this is the constant 20 decibels of your gain, alright, and then this 10 is actually your frequency, alright. It's not frequency actually. Anyway, it's not frequency, okay. So, but I want to just stress is that this is the gain, overall gain of the system, 20 dB. So what you're gonna do is actually to draw a line, straight line down, and then label this as a 20 dB gain. Alright, the next thing is gain of integrator. 1 over s is equals to 1 over omega. If you remember, s equals to j omega. Okay, but the j I ignore because it's just something to state that it's imaginary axis as well. So equals to minus 20 log omega. So this is the formula you're gonna use. So how do you plot the integrator part? The integrator part is simply which origin that you set. For me, in this case, I set my origin as minus 3 in the x-axis. And if you remember, x is equals to log omega, right? So in this axis, we are talking about x equals to log omega. Nonetheless, you can also plot in terms of the log plot, which is frequency is 0.001. So nonetheless, if you are given a normal coordinate plot, okay, normal the box one, if you remember this grid one, you're gonna use the this type bar, okay. If you are given those logarithm graph paper, you're gonna use this type. So be very careful which type of paper you're gonna use. So nonetheless, if you have, so in this case, my frequency is actually 0.001, right? So if I were to put it in here, alright, I will have a minus 60, okay. Okay, if it's minus 20 log omega, okay, minus 20 log 0.001 is actually minus 3, okay. If we were to take a look, 0.001, if I log it, is minus 3. So minus 20 minus 3 is actually equals to 60. Alright, so if I have 0.01, I'll have 40. If it's 0.1, I'll have 20. And then if it's 1, I'll have 0. Right? So you can actually work it out the table. I'll not, yeah. Right? And then this is also why that you have minus 3, minus 2, minus 1 over here. If you were to, because x is equals to log omega. Alright, so you can straight away minus 20, because it's minus 20 times x. So minus 20x. So the y-axis is minus 20x. So if you remember the rule is that for the integrator part, minus 20 log omega can be in terms of minus 20x. Right? So you can straight away use this phenomenon. So minus 20x is actually minus 20 times minus 3, right? So it's 60. So in this case, your graph is gonna have some gradient of minus 20. Alright, so maybe I should use a different color, maybe blue color. Alright, so this graph, and you can label that this is actually the integrator graph. Maybe I should label over here with a minus 20 dB per decade. Okay, so wonder why minus 20, why not plus 20? Okay, it's because minus 20 is actually the typical case for poles, right? A pole contributes a negative phase, negative system, so you have a minus 20 over here, right? And therefore, now let's plot the gain of zeros. Okay, the zeros is actually this point, this dude over here, 1 plus 10s. And if you were to head back to just now, we say that 1 plus 10s, or 1 plus 10j omega, or 1 plus 1 over 10 omega j, is the car frequency is actually 1 over 10, right? So it's 0.1. So that's why we have a 1 over 10 over here, right? So if I were to logarithm this frequency, you have minus 1. So this is the car frequency or corner frequency of the system, right? With a 20 dB per decade, with a plus. A 0 will always contribute a positive phase, right? You may wonder why, because minus 1, if I were to 20 log this one, I'll have minus 20, right? If you take a look, 20 log, I have a minus 20 gain. So it should be going downwards, right? Minus, because this is minus 1, I should be going downwards, but why I'm going upwards? Okay, why I have a plus 20? The reason is that you're only taking omega c1, you're not taking the ratio, right? The equation given is actually the ratio. So take a look, 20 log omega over omega c. So this ratio, okay, has a total gain of 20. So you always gain by 20. Also, this is simple lead, which is, is a zeros, so it's a numerator. As you can see, the denominator for the poles, the lead, the simple line is actually the ratio times minus 20. Okay, it's going downwards. So you're gonna take a look on this. So it's kind of like confusing, but yeah. So in this case, we know that the core frequency is actually minus 1. So let's plot it out. So minus 1 is actually at this point, right? at this point over here. Maybe I should use. So minus 1, I have plus 20. So per decade. So 1 decade is, okay, maybe I should write it over here first. Okay, so 1 decade, this is 1 decade. Okay, 1 decade I have 20 gain. Okay, this is what it means, the gradient. So this is the zeros. So I will label it plus 20 per decade. Right. So now likewise for the poles. Hold on. Suggest that you say that is the gain of the lead, not the zeros. Okay, it should be the gain of the lead. Sorry. Yeah. So it should be the gain of the lag also, right? So the gain of the lag is actually, if you were to take a look, the same form. Omega C2 is equals to 10, because the cutoff frequency that we have found for omega C2 is equals to 10. If you don't know, then you just head back to a few minutes ago, right? And then if I were to have logarithm again, okay, log 10, okay, maybe I should write it in just like that. So you have 1, right, with a minus 20 dB per decade. I have explained why is it minus 20, because the omega divided by omega c is simply, this one is simply the ratio. So 20, okay, this is simple lead. Okay, we're talking about lag. So lag is have a minus 20. So it always has a slope of minus 20 linearly down. So therefore we have a, because currently this is the point, this is x, okay. This thing is actually x is equals to log omega. So we are plotting the coordinate system x is equals to log omega. Right, so this is why this is why I do this in order to plot. If you are talking about the frequency graph, okay, this orange color is the frequency graph. You're gonna use 10. Okay, if it's 10, as you can see, it's actually this point over here, which is the same as log omega, which is 1. Log omega is 1. If it's the omega itself, it's 10. So they are the same plot. Okay, so yeah. So under different circumstances, you're gonna know how to use. But nonetheless, you can see the graph, the labelings are the coordinate systems. Although the labeling are the different, but then the position are the same, right? But yeah, so as I say, this is the cut frequency at 1, right? So 1 you have a minus 20 dB. So I will have a at point 1. Okay, this is the cutoff frequency. Okay, I will have a 20 dB down. Alright. So this 20 dB, if I were to label, I will label that this is actually the lag. Okay, and then minus 20 dB per dec. Right. So this is the lead, and that is the lag. Right. So this is how it is going on. This is a layout of a bode plot. Okay. Next video, I'll talk about how to draw the actual bode plot using this layout. I'll see you there.